Good evening, everyone. The event is NeuroCore. As the name suggests, it is the future of brain inspired computing. Uh, Neuromorphic chips are revolutionizing electronics by mimicking the way our brain processes information, enabling machines to learn, adapt, and operate with incredible efficiency. So, I would now invite Vibhor to start the presentation. Am I audible, guys?
Yeah, Vibhor will take the second part of the presentation. I'll take the first part.
Okay, cool. Devanu, start the first part of the presentation.
Yeah. So, hello everybody. So, right now, can everybody type in the chat box of what you think when you hear the term neuromorphic computing? Like just like a one word or like a simple sentence will do. Well, not exactly controlling computer through brain, but well, I'll introduce it right now. So, for those that are new to this, neuromorphic computing is just AI models that emulate how the human brain thinks, right? It's like a revolutionary technology, and it's critical right now, or it's very relevant right now in this current period. And because right now AI models are incredibly power hungry, whereas the brain, which is like the nature's supercomputer, only consumes about 20 watts of power approximately. So I'll go more in depth about this. Uh, so let's take a look over here. Before we talk about the silicon and circuits, we'll talk about the human brain. So the brain contains an astonishing 86 billion neurons and a staggering 100 trillion synapses. Yet, despite the incredible complexity and the processing power, the human brain runs on an average of merely 20 watts. To put that into perspective, your typical laptop charger pulls 60 watts, whereas a high performance GPU in a data center pulls around 300 watts. So there's a vast difference. And it's matters today, or it's relevant in this context today, because AI models are like power hungry. Like its emissions are comparable to 5 cars over their lifetime. So this is not exactly sustainable, right? So neuromorphic chips aim to fundamentally change this by mimicking the brain's insane efficiency and the parallel processing capabilities, offering a path towards a more sustainable and powerful AI. Now, this is where it gets truly fascinating because we're not building a faster conventional computer. We are essentially recreating how the human brain works directly in silicon. It's not an incremental improvement, but a paradigm shift. I'll touch upon why it changes everything, but first let's discuss the core design principles. The first, it's parallel processing. Think of your traditional laptop's CPU as a single chef, meticulously cooking one dish at a time. It's powerful but largely sequential. Whereas neuromorphic chips, on the other hand, are like 100 chefs working together all simultaneously, that too on different tasks. There is no waiting or bottlenecks. The massive parallelism allows them to handle incredible complex tasks and large datasets with unprecedented efficiency. Next, let's consider the ability to process the sensory data. Now, imagine a self driving car that just doesn't process its sensor data, but actually feels the road condition or perceives its surroundings like that of a real, like a human driver. It's this real time processing of diverse sensory inputs without an immense energy drain that makes these systems so valuable. Because traditional systems would be inoperable in such conditions, right? They cannot compute so much data. So these systems are largely able to do this because they excel in pattern recognition. And now I'll talk about the most groundbreaking aspect, which is the energy efficiency. See, neuromorphic chips save on power because they only power up the specific neurons or computational units that are needed for that task. It's like turning off the lights in an empty room versus keeping the lights on in a stadium for 24/7. It dramatically lowers the energy consumption and makes them a truly sustainable alternative for high performance computing. And finally, I'll talk about their impact on AI applications. We are already seeing chips that can learn new skills on the fly, directly on device, that too without needing a massive data center. Pretty soon, your smartphone might be able to handle complex AI tasks that currently require server farm, truly bringing AI to everyday devices. While we have already touched upon some of these aspects in this slide, I'll just recap some of them. Uh, First of all, we've discussed parallel processing, which is like central to the design, allowing them to emulate brain-like processing by executing many operations at once, leading to enhanced computational efficiency. It's a fundamental departure from traditional sequential processing. Then there's the energy efficiency, which is like a game changer. It can reduce power consumption, and which is actually a very important aspect for the proliferation of AI into mobile embedded systems and for promoting sustainability at such a large scale computing. But beyond these, we haven't highlighted two features, such as the real time learning, where neuromorphic chips truly begin to mimic the brain. They are capable of adapting and learning new information dynamically as it arrives, similar to how the human brain constantly learns and updates its understanding. This enables a level of dynamic performance previously unattainable in edge devices. And finally, their robustness. They just don't process data. They maintain reliable operation even in noisy and unpredictable environments that would crash traditional systems. A self driving car navigating in blinding snow, or a factory robot working flawlessly despite the significant electrical disturbance is the neuromorphic robustness in action. The secret lies in a redundant brain like architecture that keeps working even when the individual components might experience issues. They adapt continuously, making them ideal for mission critical applications where failures can result in catastrophic consequences. So, with these features, how are neuromorphic chips actually impacting the real world? Firstly, let's talk about robotics. These chips give robots advanced sensory processing and the ability to make decisions more autonomously. Picture drones weaving through complex obstacles without pre-programming, or factory bots adapting to changes on the assembly line uh, continuously. It's like giving robots a new level of perception and responsiveness. Second, they are optimizing sensor networks. These chips power a huge networks of IoT sensors while keeping the energy use incredibly low. They analyze data right at the source, providing real-time insights that are crucial for smart cities that are managing traffic, or monitoring equipment that is used by industrial facilities, or even advanced healthcare devices that are used for tracking vitals. This on device processing drastically reduces the need to send data to the cloud. And thirdly, boosting the AI performance. They make machine learning algorithms faster and more efficient and enable the chips to run AI on platforms that were previously impossible to run due to the power or latency issues. Tasks that needed a huge server farm could now run on everyday devices, truly democratizing advanced AI. In short, neuromorphic chips are already driving breakthroughs across multiple and diverse industries, pushing the boundary of what's possible at the edge. So let's take a closer look on one of the applications I just mentioned, which is the robotics. The slide over here visually reinforces exactly how neuromorphic chips are giving robots a form of like a brain. As you can see, the chips are crucial for developing advanced robotic systems. They enable the robots to process information in a way that mimics the human brain, fundamentally improving the functionality. It's not about faster processing, but rather being more intelligent and adaptive. By replicating the brain function, the chips allow robots to interpret complex sensory data effectively. It means smarter decision making in real time situations, where like whether it's understanding the terrain, recognizing unexpected objects, and even interpreting human gestures. This directly leads to the ability to enable real-time environmental interaction. Robots equipped with these chips can seamlessly interact with the surrounding, allowing them for dynamic and agile responses to various stimuli and scenarios. They are no longer rigid machines, but highly adaptable systems. Ultimately, this integration significantly improves the performance in critical tasks. Think about essential operations like complex searches, rescue missions, precision manufacturing, and autonomous exploration in unknown environments. Neuromorphic chips are enhancing robotic efficiency and capabilities in these vital areas, making them more autonomous and effective than ever before. While the potential of neuromorphic chips is immense, the field it's also a cutting edge field, and with any new technology, we face significant hurdles that need to be addressed for widespread adoption. As the slide clearly indicates, first there's the complex architectural issue. Accurately designing architecture that genuinely replicates the human brain is a monumental challenge. It demands an intricate fusion of neuroscience, understanding how the brain works, and electrical engineering, all translating into silicon models. This is an disciplinary effort that is truly at the frontier of research. Secondly, it's the integration with existing technology. Integrating with existing technology poses numerical difficulties. For neuromorphic chips to be truly practical, they need to seamlessly communicate and function with the current technological systems and established devices. Ensuring this compatibility is a complex engineering task. And lastly, we lack standardized frameworks. Without uniform guidelines for design, programming, and testing, the development and adoption of neuromorphic computing can be fragmented and slow. Establishing these frameworks is critical for facilitating consistent development and ensure broad application. There's one more challenge, that is moving from lab prototypes to high volume industrial manufacturing presents a logistical and economic complexity. Developing efficient and cost effective manufacturing processes is crucial to keep up with the potential market demand. But despite such formidable challenges, the future success depends on the solutions we develop. Addressing these issues are critical for the future success of neuromorphic computing. This will require ongoing innovative solutions and critically the collaborative effort across academia, industry leaders, and foster continuous advancement in this groundbreaking field. Given these challenges, particularly around the integration, let's discuss some important strategies being employed to overcome them. Firstly, the collaboration is essential among all stakeholders. The engagement of academia, industry leaders, and government agencies is crucial, so that by working together, we can pool the resources, share the knowledge, and accelerate progress. And secondly, we need to establish standardized protocols that will greatly simplify integration. Developing and adhering to common frameworks will enhance the entire integration process, making it easier for the chips to be incorporated into various systems and products. The key to building an ecosystem around neuromorphic it is the key to building an ecosystem around neuromorphic computing. And thirdly, investment into R&D. Robust research funding is vital for addressing the inherent complexities of this technology. It allows the scientists and engineers to explore the novel architecture, materials, and algorithms that can unlock new capabilities and solve current limitations. And finally, the pilot projects. By testing neuromorphic designs in a real world and controlled environment, we can refine their usability, identify the unforeseen issues, and gather critical data to improve the future iterations. Such practical insights are invaluable for moving from a theoretical concept to a deployable solution. These combined strategies are paving the way for a more integrated and impactful future. Before we delve into specific case studies, it's vital to understand how I will recap how neuromorphic chips truly stand apart from traditional computing, like your standard GPUs and CPUs. While conventional systems operate sequentially and consume considerable power, neuromorphic chips utilize parallel processing, often with integrated memory, leading to lower power consumption and enabling hardware based, faster learning AI models. This fundamental difference is what allows them to unlock capabilities traditional computing simply cannot match in terms of their efficiency and real time adaptability. To further elaborate on these distinctions and explore the real world examples, I'll hand this over to my friend Vibhor, who will guide us to the next phase of the presentation.
Uh, Thank you, Devnush. Now I'll be taking over. One second. Okay. So uh, now this slide shows that the comparative performance of metrics, neuromorphic versus traditional computing. So as Devnush just highlighted, neuromorphic computing offers a fundamentally different approach. To truly grasp its significance, let's look at some comparative performance metrics analyzing the efficiency in AI applications. This slide provides a clear snapshot of how neuromorphic chips stack up against traditional CPUs. First, consider processing speed. Traditional CPUs, while incredibly powerful, are largely sequential processors. They tackle tasks step by step. This is why their processing speed is typically categorized as moderate when dealing with complex parallelizable tasks. Neuromorphic chips, however, are built on high, inherently parallel architecture. They can process vast amounts of data simultaneously, which is their core strength, especially when emulating brain functions. Next, let's examine energy consumption. This is a critical factor in today's computing landscape. Traditional CPUs are known for high energy consumption, often needing significant power and cooling, which contributes to substantial operational costs and carbon footprints, particularly in large data centers. In stark contrast, neuromorphic chips are designed for low energy consumption. Their event driven and sparse activity models mean they only consume power when a neuron fires, similar to biological brain. Then we have adaptability. Traditional CPUs, while versatile, generally have low adaptability in terms of learning and adjusting on the fly. Their core architecture is fixed, and changes to the behavior primarily come through software updates or new algorithms. Neuromorphic chips, on the other hand, boast high adaptability. They are designed to learn and adapt in real time directly on the hardware. Finally, let's talk about the speed of learning. Because of their architectural design that mimics neural networks, neuromorphic chips offer fast learning capabilities. They can absorb and integrate new information much more quickly than slow traditional systems, where learning typically involves extensive iterative training processes on large datasets. This speed of learning is revolutionary for applications that require constant adaptation, such as autonomous systems or personalized AI. The transformative role of neuromorphic chips in AI. Having seen the performance metrics, let's now dive deeper into the specific ways neuromorphic chips are transforming the field of artificial intelligence through the upcoming case studies. Their very design makes them inherently suited for many AI workloads. Exploring case studies in neuromorphic innovations. It's one thing to talk about the theory behind neuromorphic computing, but let's look at how it's already transforming real world applications. A standout example is the Stanford neuromorphic chip. These chips are designed to directly emulate brain like processing and have shown impressive results in image recognition. Their efficiency and speed make them ideal for computer vision tasks in areas like autonomous vehicles and surveillance systems. What's key is their hardware level integration of neural networks, pushing the limits of what's achievable in real time processing. On the industrial front, we have IBM's True North chip, a landmark in neuromorphic architecture. It features a massive network of digital neurons and synapses and is engineered for ultra low power consumption. It's, it's been successfully used in scenarios requiring constant real time sensory analysis like smart sensors, voice assistants, and embedded AI. Its efficiency enables long-term use without frequent recharging, making it perfect for AI at the edge. These case studies highlight the real-world impact of neuromorphic technology. We are not just theorizing anymore. These innovations are already solving by delivering speed, efficiency, and power-conscious AI. Finally, it's important to note that neuromorphic innovation is dynamic. Researchers are constantly refining these technologies to address complex computational challenges from data analytics to robotic control, making neuromorphic computing a key enabler of the future. Exploring future directions in neuromorphic research. So, where do we go from here? The field of neuromorphic computing is incredibly active, with several exciting future directions in research that promise to unlock even greater potential. First, a major focus is on enhancing chip scalability. While current neuromorphic chips are impressive, scaling them to truly match the complexity and capacity of the human brain or even larger biological systems is a massive undertaking. Research is heavily invested in finding new materials, fabrication techniques, and architectural designs that can support billions, even trillions of artificial neurons and synapses on a single chip, making them suitable for the more demanding AI workloads. Next, we are seeing strong efforts towards integration with software ecosystems. For neuromorphic hardware to be widely adopted, it needs robust and user-friendly software tools. This includes developing new program models, compilers, and frameworks that make it easier for developers to design, train, and deploy AI applications on these specialized chips. Improving this interface will be crucial for accelerating adoption and innovation. Another promising area is the development of hybrid computing architectures. This approach combines the strengths of neuromorphic chips with traditional computing systems. Imagine using neuromorphic chips for highly parallel, energy efficient pattern recognition and learning, while offloading sequential, high precision numerical computations to conventional CPUs or GPUs. This hybrid model could offer the best of both worlds, leading to more versatile and powerful overall computing solutions. Finally, significant research is being dedicated to the development of learning algorithms, specifically optimized for neuromorphic hardware. Traditional AI algorithms are often designed for von Neumann architectures. New learning paradigms are needed that can fully leverage the unique features of neuromorphic chips such as sparse, event driven processing, and local learning rules. This will lead to more efficient, biologically plausible, and scalable AI models that can truly harness the power of this new hardware. These directions represent the cutting edge of research, driving us towards a future of ubiquitous intelligent computing. Ethical considerations in neuromorphic computing, addressing challenges for responsible development, navigating the ethical landscape of neuromorphic technologies and the social impacts. As with any transformative technology, especially one that mimics human intelligence, neuromorphic computing brings significant ethical challenges that must be addressed from the start. First, establishing clear ethical guidelines is essential to ensure these systems are developed responsibly and reflect societal value. One major concern is data privacy. Neuromorphic systems process vast amounts of data to learn and adapt, which raises serious questions about how that data is collected, stored, and used. Ensuring secure, privacy respecting handling is critical. Next is transparency in decision making. As these systems become more autonomous, it gets harder to trace how they make decisions. For high stake areas like healthcare or autonomous vehicles, transparency is vital to maintain trust and accountability. We must also address the risk of algorithmic bias. If neuromorphic systems learn from biased or unbalanced data, they can unintentionally reinforce societal inequalities. Ongoing monitoring and fair data practices are crucial. Lastly, there's the need for alignment with societal norms. These systems should evolve in step with ethical standards and public expectations. This requires collaboration among technologists, ethicists, policymakers, and the public. By addressing these ethical concerns early, we lay the foundation for a responsible and beneficial future for neuromorphic computing. The future of neuromorphic chips in computing, exploring transformative potential in AI and robotics. So what does so what does the future hold for neuromorphic chips in computing? This slide encapsulates their immense potential and the path forward. At its core, neuromorphic computing signifies an exceptional energy efficiency. This remains a cornerstone of its transformative power. They consume less power compared to traditional chips, which is a game changer for sustainable computing and widespread AI deployment. Their versatility can transform various fields of technology. We've touched upon robotics, sensor networks, and general AI performances, but their applications span across AI, robotics, and many more. From medical devices to smart infrastructure, military applications, and beyond. They provide significant advancements in processing efficiency, offering solutions for complex computational problems across diverse sectors. However, to fully realize this potential, ongoing research and development is crucial. The field is still relatively young, and continuous investment in R&D is essential to refine architectures. One second, one second. Sorry, I had to give the attendance. That's fast. Okay, so I'll continue. There were ongoing research and development is crucial. The field is still relatively young, and continuous investment in R&D is essential to refine architectures, improve manufacturing, and develop new algorithms that fully leverage these chips. Addressing issues will unlock neuromorphic technologies' full potential. In essence, neuromorphic chips signify a breakthrough in computing. They represent a paradigm shift, moving beyond the limitations of traditional architectures to create systems that are not just faster, but fundamentally smarter and more efficient. And while the future is bright, overcoming challenges is key to success. As we discussed on slide 7, challenges related to architecture design, integration, standardization, and scaling production must be continually addressed through collaborative efforts and innovative solutions. The continued success and widespread adoption of this technology depends on our ability to navigate and overcome these hurdles. This is truly where the future of computing is headed. Once again, I'll explain a bit more in detail about traditional versus neuromorphic computing. To summarize and reinforce the core differences we've explored, this slide provides a direct side by side comparison of key aspects between traditional and neuromorphic computing. This distills the technical distinctions into a clear summary. When we look at processing, traditional systems are inherently sequential, executing tasks one after another. Neuromorphic systems are parallel, processing many operations simultaneously, much like the brain's vast network. Regarding memory, in traditional architectures, memory is typically separate from the CPU, leading to the need for constant data transfer. Neuromorphic chips often integrate memory directly with the processing elements, minimizing this data movement and speeding up operations. For power consumption, traditional systems are typically high power consumers, often requiring 100 watts or more, whereas neuromorphic designs are engineered for low power, often operating in 1 to 100 milliwatt range. And finally, learning. Traditional AI relies heavily on software based learning, where algorithms run on general purpose hardware. Neuromorphic chips, however, are built for hardware based learning, enabling on device adaptation and continuous learning with greater efficiency. This table effectively highlights why neuromorphic computing is not just an alternative but a necessary advancement for the future of AI and intelligent systems, offering distinct advantages where efficiency, real time learning, and complex pattern recognition are paramount. Join us in shaping the future of computing with neuromorphic technology. It is crucial for both students and professionals to engage with these transformative innovations. As advancements in neuromorphic technology continue to reshape the landscape of computing, it is incredibly crucial for all of us to engage with these innovations. By understanding and leveraging the unique capabilities of these technologies, we can pave the way for a more efficient and intelligent future in artificial intelligence and machine learning. Journey of neuromorphic computing is a collaborative one, requiring interdisciplinary efforts and a shared vision. This isn't just about building faster computers, it's also about building smarter, more energy efficient, and more adaptable systems that can tackle some of the world's most complex challenges. Let's work together to push the boundaries of what's possible and shape a future where intelligence is ubiquitous and sustainable. Thank you for your attention. Now, in a few minutes, we'll post a Google Form link in the messages, in call messages, and everybody will be given like 10 to 15 minutes to attempt it and submit it by the end of this session. I've posted the link in the text box. Those who want to attempt can do it. So, we would like to conclude the session here, and I hope everybody gained something or the other type of knowledge about neurological computing, as it's a topic that is quite complex, and whatever we explained was just like whatever we explained was just a small part of it. So yeah.
So, thank you guys for joining us for NeuroCore. We hope this session has given you valuable insights into the world of neuromorphic chips and their transformable potential in modern technology. As we continue to push the boundaries of innovation, let us remain inspired by the brilliance of the human brain. Stay curious, stay connected, and we look forward to welcoming you in our future sessions. Thank you very much.